Oh boy. Z values. The Z value. Okay, so Z values are actually pretty simple. Z is equal to x minus mu divided by little sigma, whereas x is the lowest data. Okay? The lowest number. Okay? Alright, so far we were dealing with that string of numbers. Remember? We dealt with
3, 6, 8, 11.
3, 6, 8, and 11. Okay? That's our x's. So our low x, and we'll just say our low x is 3. Okay? And from our previous problems, we were able to construe that. So we need some certain things. We need our low x. We're going to mark that as low x. Okay? It just says x, but I'm going to put a little arrow out in front. I'll make that in red, so you know it's different. Okay? But it's just saying that, you know, it's our smallest x.
And mu is 4.
And our mu isn't 4.
Is it 1?
Mu was 7, remember?
Oh, okay, so
Mu we found to be 7. And then our
little sigma?
our sigma, or our population standard deviation, was equal to 2.9154759, right? But that's why we also did it the other way. Or mu was equal to the square root of 34 over 2. Right? It's the same thing. See, this is a real number. And when we plug it into new things, we like to use real numbers, not approximate numbers. Approximate numbers leaves room for error. Alright? The more error you leave room for, the more error you create. Okay? And a little error goes a long ways. Okay? Believe me. When you're dealing with things like the Hubble telescope, okay?
yeah.
You make a small little tiny error, which they did. I've told you that story before, right? When they're making the parabolic curve out of the mirror, it has to be exact. I mean, perfect. So they're doing everything exact, creating this parabolic curve. It has to be the exact parabolic curve so that when the rays come in from the lights and everything comes in, it points it back at, so that when it's what it's looking at stays in focus, right? Okay, makes sense. Simple, little like a little camera, right? Okay, so they're doing it. Well, where did we do it? On Earth, right? Okay, well they took into consideration of the Earth's gravitational pull. No problem. Except for one thing. They took into consideration the Earth's gravitational pull at sea level. Well, where they did it was at like 4,000 feet in the air. Not a big difference. But when they shipped that Hubble telescope out into the space, what happened? Everything came back blurry. Why? Because even that small amount of difference with the gravitational pull from sea level to 4,000 feet, or wherever they were, 6,000 feet, just that small amount of difference caused a huge amount of error. When you're talking about a dish, something that's trying to find something that's millions of miles away. I mean, you're not talking about just looking at the moon. You're talking about trying to look at these objects that are millions of miles away. So when you're talking about air at millions of miles, now all of a sudden you increased your error 10-fold, 12-fold, So that's the problem. Using approximations can cause issues when you're dealing with things that small things matter. Like, I don't know, maybe things at a molecular level, right? So when we're talking about atom bombs and dealing with stuff on the molecular level, all right, we need to really be careful with our stuff, okay? When we're talking about space travel, we need to really be careful about our stuff because a little error goes a long ways, okay? So that's why I like to teach real numbers, the actual number, okay? So, what do we need? We need x. We got it. What do we need? We need mu. We got it. What do we need? We need sigma. We got it. Okay? So now we just plug them in. Okay? So, z is equal to x, which is 3, minus mu, which is 7, all over the square root of 34 divided by 2. Okay? So,